I can't just say we're an AI company, because we are that, of course, but we're not an AI company like any other, especially today when the term artificial intelligence means or is used more or less interchangeably with machine learning. They've become almost the same thing. And at New Sapiens, we have nothing to do with machine learnings. So you need to reset right from the beginning. But another reason I hesitate is that I've been in the field. I won't even tell you how long ago I got into AI, when I was working on the Hubble Space Telescope. But I've never seen the field to be so have so much hype and exaggeration and downright misinformation going on as it is today. So what I usually do to try to get into it, I'll ask somebody a question of my own, and I'll say something like, did you know that chatbots like Amazon's Alexa or Apple's Siri really don't understand a word you say to them? And usually I'll get a nod, and oh, Siri just answered me. Siri just said, I'm not sure I understand. But some people actually say, really, I didn't know that. And I guess those are the people who actually never tried to interface with Siri or Alexa. But it's actually pretty easy to demonstrate what I'm talking about. For instance, let's say I was going to give Siri a very ordinary, simple declarative sentence that any 5-year-old would understand, like, I'm taking my Tylenol now. Okay, well, Siri doesn't know what that means. Couldn't comprehend that statement. Wants to search the web for me. No thanks, Siri. How about another one? How about a canary is a cute little yellow bird? Here's what I found, she says. Well, I said it was a cute little yellow bird. I didn't want Siri to look up something on the internet. So you begin to see what Siri really is. Of course, it's a text-based front end to a search engine. That's really what it always has been. It's what it's designed to be, what it still is. And so it's looking for some keywords and mapping. Let's try something else. Jeff rides scooters to work. Looks like you don't have a work address listed on your contact card. So again, work, the key word, do something. Somebody wrote some code in there that said if they start talking about work, map it to the contacts and look about their work address. So that if you do use Siri and you learn how to use it, it is useful for certain things. But the notion that it comprehends language, it's kind of nuts. I mean, it's just not there. And we can talk about these if you want, but that really goes just as well for the large language models like GPT-3 that we hear so much about. Of course, if you are following at all, you've been following the recent controversy about Mr. Blake Lemon, if that's his last name, who's claimed that one of the language models he's been working on at Google is actually a person, sentient, actually understands what's going on, understands language, has feelings, has emotions. He says he hired a lawyer for it because it was being mistreated. But anyway, it's on my mind. I just finished writing a blog article about that, about AI and magical thinking. It's on my blog website, Forward to the Future. But anyway, these programs, to them, text, they talk about text generation, like these language models, text generators, or chatbots, or digital personal assistants. To them, words and language are just patterns of ones and zeros. And somebody has to write code to handle specific ones or zeros, or to pick the patterns out and then to do something with them. And that's why Amazon has 10,000 people working on Alexa. because they wanted to understand a lot of things that people might say, so that requires custom code. So, so what would it be like to talk to a program that does understand language in the same sense that that we do? And we'll talk a little bit what that means. But at New Sapiens, we created a technology, and it results in digital entities that we call sapiens, and I'll say some of the same things. So when we talk to somebody who understands what we're talking about, and you just give a declarative sentence, you usually say, uh-huh, you know, to let you know that they got it. Or so I talk to my sapien Helen, and if I say, how about, when did I take my Tylenol? Because that's really the point of telling it I took Tylenol in the first place. And Helen would say, you ingested Tylenol at 10 o'clock in the morning on this date. Now, that's a perfectly intelligible answer to that question, given that I told it earlier that when I took Tylenol. But note here that it responded with ingested rather than take. That's because it's looking up the meaning of words, and it's not the meaning of words, but it's relating words as symbols to knowledge that it already has. And in the context of medications, the word take doesn't mean take, it means to ingest. So what is a canary? Cute little, they are yellow birds that I think they're cute. So that's right. But it's interesting when you look at that, in the grammar, in the sentence, cute and yellow are adjectives, and we're taught in school that adjectives modify nouns, in this case, canary. But in this case, Helen's understanding of language goes beyond the grammar. Why? Because cute, when you think about it, is not really a property of a canary. It is an experience in the observer. It's an subjective experience, not a property of the canary. And suppose I told Helen, for instance, that Jeff rode scooters to work, but it doesn't know what a scooter was. We'd give a dialogue like this. Then I say, what's a scooter? And it says they are probably vehicles, possibly horses. So what happened here? So Helen has inferred that a scooter is probably a vehicle or maybe a horse because it knows something about the action of riding and what riding entails. And that means that if it knows about riding, it understands that only certain things can perform the action, and only a certain set of things can be the object of that action, So that's rather profound. You know, it's estimated that a 5-year-old child has a vocabulary of about 2,500 words, whereas the average college student has a vocabulary of about 30,000 words. So how many of those words are actually learned on a vocabulary test, looked up in the dictionary? A tiny fraction. So human beings are sponges for new vocabularies, which they pick up from context, and so are sapiens. And of course, sapiens have perfect memories. So sapiens are not language apps, and they're certainly not chatbots. They comprehend language in the same sense that humans do, because we found them a practical way to curate knowledge from human minds and make it computable in machines. So what we've done is we've given them knowledge of the common sense world sufficient to understand the meaning of the words, but that's really just the beginning. So that's what New Sapiens is about. We're not about data science at all. We're about knowledge. So let's talk about knowledge and language a little bit. If if knowledge, well, let's start with language, because it's important to understand when you say, I've given you a demonstration, of course, you don't really know what's going on in the software. But just stand back from that and think about language in the sense of as you read it in a book, or as you write something, or as we're having a conversation. So if I want to communicate an idea, a concept, like canary is a little yellow bird, I first have to take that idea of the canary and I break it down into simpler ideas, and they have to be ideas that I think that if the person I'm communicating to already has in their minds. So I think that, okay, what is a canary? It's a bird. It's a subclass of bird, and they're small compared to other birds, and they're yellow. And I may throw in that I think they're cute, but that's neither here nor there in defining what it means. So then I pick out symbols that I have for those ideas. I arrange them in a grammatical formula, a syntax, which is an encoding. And I ship that to the person through writing or in conversation. And that person takes those symbols that they also have. A canary is a cute little yellow bird. And they relate the words to ideas they have. And then they look at the grammar and syntax, and that's like the assembly instructions to put together the new idea. So language is a communications protocol. It's not, it doesn't contain language. I mean, excuse me, it doesn't contain knowledge at all. It's not in there. So what's in books? Knowledge doesn't contain books, it contains language, which is a communications protocol. The Library of Congress has no knowledge in it. It just has a lot of language in it. The knowledge doesn't happen until somebody comes along who knows the code and decodes it, right? So unless you have the knowledge to relate the words to symbols to already and can assemble them and know the code, you're not going to get the knowledge. And so the knowledge only becomes alive and real in a mind. The language is just the communications protocol, which means if you do numerical analysis or statistical analysis, like language models GPT-3 does and the others, you can do analysis of the communications protocol all you want, but you'll never get knowledge. You'll never get comprehension because it isn't in there. So what is knowledge? Well, knowledge is a model. That's not controversial, is it? It's a model. It's a model in the mind of the external world. And a model is a very interesting kind of information structure. It's one that resembles the thing of which it's a model. A model has the relationship to something. It's a model of something, right? So this relationship of model to prototype. And knowledge is a model of the world, of things in the world. So those models tell us about the world. But models aren't made out of symbols. You're familiar with the first wave of AI is called Symbolic AI. And they were attempting to achieve knowledge by putting and manipulating symbols in the machine, but they never succeeded. I know I was one of those people who tried. In my first company, we used a rule-based expert system. But symbols, here's a symbol. Does anyone know what the symbol is a symbol of, or was it its reference? Probably, if you have some chemistry. It's a formula for the glucose molecule. It's telling me if you know it, if you know what the symbols stand for, you can decode some information, but you have to decode it. It's 6 carbon atoms and 12 hydrogen atoms and 6 oxygen atoms. And that's all it tells you about the number of atoms, but you have to decode that. If you wanted to write some software, of course, you'd have to write a lot of code to map each one of those symbols into its reference, and then you'd have to manipulate the references. A lot of code. Now, this is a model. of a glucose molecule. And as you see, it's not a symbol because its relationship to the molecule itself is not arbitrary. It resembles, in fact, to be even more precise, this is a picture of a picture of a model of a glucose molecule. But that's okay, because pictures are models as well. And in fact, now you begin to see the difference between symbols and why symbolic AI failed. It's the same as the difference when we say a picture is worth 1,000 words. Because you immediately can look at the picture, you can immediately can grasp that model and learn something about the reality of it. And if you look in your own mind, which if we're going to get enabled to transfer knowledge from our minds into computers, we have to start with looking at it in our own mind. We find that our notion of a tree and the model of it we have in there, our model of it isn't any different if we speak German than if we speak English or Spanish or any other language. It is the same. So knowledge isn't made up of symbols in the human mind nor in computers. And you never will get there that way. So what did we do? How did we achieve this? Well, we have a model, a methodology and a system that you might call cognitive chemistry. And it's a way to achieve knowledge in a machine that is scalable. That means it's practical, that you can keep adding more and more and more of it. And it gets more and more powerful, actually, for less effort, rather than tailing off the other way. We certainly found with expert systems that they weren't scalable. You'd always start off well, a little while, but pretty soon you have to do more and more work to get less and less performance. And eventually it tailed off to the fact that you never reach your goal. You could put an infinite amount of effort in there and you'd never get to the level of performance you needed for many practical applications, including analyzing telemetry for the Hubble Space Telescope. So if you look back in your mind and you look at the ideas and the knowledge there, you see that complex ideas are composed of simpler ideas. And that leads you to the conjecture of Democritus, who imagined atoms, because he said if you take a material object and you break it into smaller and smaller pieces, it seems reasonable that you'll eventually get to a piece where you can't get it any smaller. And he called those atoms. So we asked ourselves, we looked at these complicated ideas, and we take the idea of canaries and we break it down into smaller and smaller and smaller parts. And how small a part can you get to? And what do you have when you have that? You would get to ideas that were so fundamental that you couldn't break them down into sub ideas that were smaller than that. And we found an interesting heuristic for that, by the way. Fundamental ideas can't be articulated the way I just described to you as communicating in language. For instance, the relationship between a model and its prototype is one of those fundamental ideas. You can't describe it. I mean, you can't just give a model is X or the relationship of a model is X. You have to give examples. Well, here's a model, and here's a model, and there's another model train, a model airplane, and you say, oh, I get what a model is. So it turns out that there are fundamental ideas, which are the basics of knowledge in our minds and potentially in computer memory. And they're of a reasonable number, 100 or so. And if you know what those are and you examine them, then it raises the possibility that you could classify them, those fundamental ideas, and the classifications themselves are fundamental, such that you could predict ahead of time whether an assembly of ideas made out of certain fundamentals could connect to another one. In the same way, the periodic table will tell you that you cannot connect an argon with a neon molecule. However, a sodium and a chloride molecule will connect with very readily. And if you could do that and you're trying to do that code, you've really solved the problem. So we've created something we call the cognitive core. This is kind of a cartoon in it, which in one sense, the vertical columns could be considered the type of parts. For instance, imagine that knowledge, and with these fundamental ideas, and you make them like atoms, and you take the atoms and you create, molecular structures out of multiple atoms. For instance, the model of a canary would be like a large molecule or assembly of molecules put together in a certain way. But that the vertical columns here would tell you that the type of the parts of the model pieces that you have to use to put together. And it turns out there's only about 10 of these. And they're like pieces of the jigsaw puzzle of a given shape, because a jigsaw puzzle may have a million pieces, but there's only 10 different basic shapes in a jigsaw puzzle, right? And they only go together in a certain way. So what we're talking here on these vertical columns, when you apply that to knowledge or knowledge about knowledge, it's more like the notion, the difference between a quality or a quantity, or an action and the result of that action, or a relationship, or the things out there that have properties that exist in themselves. Whereas properties, ideas which are properties of things, have to be properties of something. So all those are the types of things we've arranged in our vertical columns. But the horizontal columns are more like kind of the structure of reality itself. And what I mean by that in terms of where knowledge comes in, there are 4 fundamental delineations that you can make about reality as humans can wrap their minds around it. One is what we think about the things out there that exists independently of the humans, that if you took the humans away would still somehow exist, and we can think about what they would be like independent of us. Which is problematic. Well, we can through science mostly, we can come up with models of these things that work pretty well for us. But then a whole nother aspect or perspective or creation that we have to deal with is how we perceive these things. Yellow is a perception, right? But it's perception of something down below. It's down in that layer of the things in themselves. We understand light to have wavelengths and to be emitted or reflected from molecular structures. That's our knowledge of the things themselves, but we perceive it as the color yellow. And we live in that world of perceptions. And most things we live in it so comfortably that we seldom bother to make the distinction between our perceptions of things and the things themselves. So that's 2 major categories, which are in these layers. And then we have a whole nother response, which many of our ideas and many of our words putting those ideas are in that 3rd layer. And that is what we call experience or subjective feelings. How I feel about canaries being cute. It's a pleasurable feeling, makes me smile. Canaries make me smile because I experience cute. Now, somewhere along this, in these layers, and then there's sub-layers, but one of these layers is where cute, the model of cute, gets categorized. And that tells me, by the way, that it's not a perception, a sensory perception, and it's not a thing in itself, or it's not an inherent quality of the thing itself, which is the canary, but it's an experience in the human mind. And finally, we have our ideas, our intellect, our sapience, as we call it, as opposed to our sentience, which is our subjective feelings. And that's the ideas, the models that we carefully put together through science and through language. So if you want to understand language, if you want to understand the world, if you want to model the world, you have to go through all this. And that turns out to be immensely powerful. So putting the G in AGI, we used the example, I think, I said that Jeff rode a scooter to work. And this is a picture of a information structure in our model of the action of writing. Action's one of those verticals, and writing is in an appropriate level of the perceptible world, an activity that people do. And it is defined as a structure. It has a relationship to a set. Actually, no, in this case, it's not a set, it's an actual class of things, people. And that relationship, its fundamental idea, is defining for what things can perform this action of writing. And another one it has is pointing to a set. In this case, it's pointing to several of them, the set of vehicles and the set of horses. Actually, in a more well-developed model, we just have a set of writable things in which vehicles would be there as a subset, and then there would be a set of writing animals, of which horse would be a subset of the writing animals, along with elephants, and we'd be able to put other knowledge on there about the distinctions about where you ride elephants and where you're most likely to be riding a horse. And all that stuff is quite easy to add to our model. It doesn't take any programming. None of this is in the code. So there's no rule. There's no executable code. There's no statements in our software that have anything to do with people or writing or animals or horses. It just, the code is just the same lines of code. The same lines of code. Here we use a few lines of code reference this structure. When I said Jeff rides a scooter to work, and the Sapiens didn't have a reference for the word scooter. So it used this simple structure to infer the meaning and to create a new concept, which was a concept that it knows it has the word scooter symbol pointing to it, and it is tentatively identified as either a kind of vehicle or a kind of horse. But doesn't know yet. But later on, somebody will say more about scooters, and it'll say, oh, it couldn't be a horse. It's got to be a vehicle. But suppose I said, Jeff rode a canary to work. What would it do? It would come back to me and it would say, I have a problem with what you say. Canaries can't be ridden. Not in this set. And I'd say, why not? It said only people can ride. No, I'm sorry. We're talking about riding the scooter, the object. It would say only vehicles or horses can be ridden. So in this one little information structure, and again, the same lines of code, because we have about 2,500 or 3,000 of these same kind of structures in our model, and they're all connected together through that classification scheme. But the code that learns the meaning of new word from these structures is just 2 or 4 lines of code. And it'll learn, you're on a fast track from that, from 25 or 3,000 words to 30,000 words, just through conversation, if you never even did any more modeling. And because, by the way, the ones we put in there, those 3,000 ones, have a very strong mapping to the vocabulary of a 5-year-old, or simplified versions of English, like Simple English or Basic English, which are quite adequate for communicating almost anything you want. You build up simpler ideas, you use it to build up more complex ideas, and you learn vocabulary as you go. So, but it's also the same structure that exhibits common sense. You can't, Jeff couldn't have ridden a canary to work. Common sense, most of what we call common sense is, of course, really common knowledge. So already we have common sense, and we have the ability to explain our reasoning, because the reasoning is very simple. You just go back and say, well, because it didn't fit the criteria. So all those things, common sense, natural language comprehension as humans do, and ability to explain its results, all things that machine learning can't do even a little bit. Now, people say, well, how did you guys do this? Why was it you and not somebody else, especially when the somebody else's out there have so many more resources than you do? Well, it turns out that the whole enterprise of artificial intelligence, as we have known it, may have been on the wrong tack from the very beginning. And that very beginning is the Dartmouth Conference in 1956, where the term artificial intelligence was first coined. And this is a quote from the proposal for that conference, which established what it was about. And so as you see, it is based on the conjecture that any aspect of learning or any other feature of intelligence, of course, they meant human intelligence, because that's the only intelligence we're aware of at this point. Any aspect of human intelligence can be so precisely defined that a machine could be made to simulate it. Well, okay. But it should have been called imitation intelligence then, I think, because that's what it has been. And that's what it has been. The two great waves, the first one, symbolic, really was about emulation of logic using symbols, but logic is about symbols as we abstracted out. So they wanted to logically manipulate symbols. And so logic, though, of course, is an aspect of human intelligence by which we create the end goal here. And the end goal, of course, of this whole enterprise is to put knowledge into machines, to put models of the world into machines so that they can powerfully interact with reality the way we do. And of course, the larger goal is to create a tool that's so powerful at that it can combine, that it can do it as well or better than we can. And that's what will result, or is resulting, when you combine the ability of knowledge that humans have with the power that they don't have, which is the power of computers with their connectivities and their speed and reliability and repeatability and perfect memories. And of course, then we went on to machine learning, when that's the second wave they call now Connectionist AI. And that's really not even based on so much the way that our brains create knowledge, so much as it's really going even farther back, looking at the structure of our brain as an information processor. It is a neural network. So machine learning, all of it is based on a programming paradigm, which is a direct emulation of a neural network. It is an attempt to build an artificial brain. And so what did we do? We didn't do any of that. So there's a philosopher named John Hopkins, and he, back in 1956, he said there's a whole nother way of approaching AI. Instead of imitating natural intelligence, try to find an engineering way to create the same thing in a machine, but not the way nature did it, through an engineering thing. And he made the analogy of a synthetic diamond, as opposed to an imitation diamond or a rhinestone, if you will. Rhinestone looks like a diamond, but it doesn't really have any of its desirable characteristics. It's not a real diamond. But a synthetic diamond is a real diamond. It's the same perfect carbon, perfect lattice that a diamond has. It is a diamond, there's no question about it, but it is not created by natural means. It's created in a laboratory by engineered means. It's an engineered diamond. And that's what New Sapiens has done. We've engineered knowledge as an information structure in a machine without having to go through the messy business of trying to build an artificial brain. Because think about how hard that is. Recently, with the conjecture that maybe these big neural networks might actually already have somehow spontaneously developing sentience or intelligence, you really have to go back and look at what's going on in these computers, and you really have to look about what it means to try to not only to emulate the human brain and emulate the natural processes by which the brain creates knowledge. And you realize that you would have to recapitulate millions of years of neurocognitive evolution, because the brain is layer after layer after layer after layer of processing, and it just didn't happen. It was engineered by evolution over millions of years. And if you're ever really going to get in an artificial neural network to get that kind of thing to happen, you're going to have to somehow recapitulate and understand and build those layers into your neural network so that the processing bubbles up. So they're really trying to create an artificial an imitation animal, an intelligent animal, in order to create knowledge, the end product that we're looking for. And boy, is that the hard way to do it, because the human brain and the human mind together, when you consider the brain and its functionality, the processing functionality together with its structure, it's the most complex thing we're aware of in the universe. So no, it's not going to, nothing you do with these language models or big neural networks, doesn't matter how big. Intelligence is never going to spontaneously occur. You're going to have to build it up layer by layer by layer. That's why AI luminaries like Gary Marcus out there, who gets a lot of press time, called Greg LeMond's conjecture about the language model nonsense on stilts. Of course, the interesting thing about that is that LeMond didn't do it as a scientist. He did it as a mystic. And he said, who am I to tell God where he can put a soul? Well, that's fine. But if it was going to put it in a machine, then I would expect to see the software be a lot more complicated than it is with these language models, which are basically just statistical things. They shouldn't be called language models. They should be called language sequence models, because they're all based on the Google's transformer algorithm, which is just statistically guessing what the next word should be, or what's the probability given a word, what the word ahead of it and word behind it would be. And from that, you can expand it to generating whole bunches of text. You know, one of my favorites on that was when they said, somebody said that they fed into GP3. They said researchers were amazed to discover a society of unicorns living in a remote Andes valley, and that they spoke perfect English. And so GPT came out and it said, yes, and they had wore Christian Dior makeup and had wonderful hairdos. And it was like, I felt like it was very unsettling when you read that. It was like you're getting an image from the ghost of all those people in the data set. But of course, it had no idea what it was talking about. For fun, I took that same phrase about the unicorn spoke perfect English and had Christian Dior makeup, and to a sapiens, and Helen said, I have a problem with what you're saying. Unicorns can't speak. Common sense. All right, well, so why is this the fast track? Well, here's the cool thing about this, is that we don't see any limitation. We have a very efficient way. We have a very, our cognitive core is kind of like DNA is to the specification for a living organism. All you need to do is take that, give it the necessary things, and you can build knowledge and knowledge and knowledge and knowledge. So we've got the fundamental premises down, and we've now got, it's not a product, it's a technology. It's really a new way of programming computers, and it's as important, and we feel, or comparable in what it's going to do in terms to change our society, as the steam engine was at the beginning of the 19th century. It wasn't a product, And it wasn't, it disrupted sailing, manufacturing, transportation, you name it. They were never the same again. And ultimately the way people lived. So it's not just a product, although we are building a product and we're building multiple products. We probably won't have time to talk about that. But why we feel so confident that this is going to go right up there is the fact that it's an engineering process that once you have the fundamental breakthrough, it's a straight line. It's just direct iteration on that. And it's equivalent to in architecture, when someone discovered or invented, I like that discover/invent, because that's very much the way we feel and what we've done. Discovered things about knowledge, and yet we're inventing something to process that, to apply it. So it is applied, it is engineering, and it's got tons of applications. But once you had the arch, then it was a direct iteration from arches to aqueducts, and from aqueducts to the Pantheon, and on that to the medieval cathedrals. And it didn't even require any more breakthroughs. In fact, it didn't require any more science. It was just direct engineering, good, solid engineering. And we don't see any difference or any milestone. And in fact, with this a few years from where we are today, we'll be talking, I think, human level intellect. So thank you. I think we have time for questions now.
Feel free to unmute yourself, or you can pop a question in the chat and either Daniel or myself can read it out for Bryant.
Oh, I've got a question, if that's okay.
Sure, Mike.
First of all, I really like the design that starts with first principles. I heard some echoes of Aristotle and Kant in there, the thing in Noumena. This is exactly the kind of architecture I've long envisioned.
You're exactly right about Kant and Aristotle. Aristotle's those vertical columns on our table, they came right out of Aristotle.
That's it's a great. Basically, that's kind of my idea too, but I haven't worked it exactly like that. But anyway, the question I had was regarding. I mean, one of the big difficulties with AI has long been the combinatorial explosion. So where deep learning really excels is as a pretty good tool to kind of fight the combinatorial explosion, handle the fuzziness and such. So how do you envision your architecture handling the combinatorial explosion?
Well, we don't have one. The combinatorial explosion was really, that was characteristic of the symbolic AI. And one of the problems is that they didn't really have a model of knowledge. They didn't never achieve knowledge. They just had a bunch of facts, right? And each fact was in a rule. And then the rules connected to each other through inference. So they were doing inference. So as soon as you got above a couple hundred rules, the number of possible combinations, became an explosion, and you couldn't manage it. You just couldn't manage it. Again, that's the fault of symbols. We don't have that. We have a very carefully engineered compact model. And the core model, the cognitive cores we're talking about, is only got several hundred very carefully connected elements. Everything is referenced to those. Our common sense model of the world, again, completely independent. There's no rules. There's no knowledge in rules. There's no rules embedded in the code. The code is completely agnostic to the model. So it's just straight line execution. And to give you a sense about that, And by the way, machine learning has its own problem. It doesn't have it doesn't have a combinatorial explosion problem, but it still has a scalability problem that you need bigger and bigger data sets to get better and better performance. And in fact, I would say that the scalability problem there is equally or worse. Although if you can use the patterns in the data set you have, and that's useful to you, well, you're golden. Although they're really expensive to create, as you know, they take a lot of energy, a lot of computing power, supercomputers running for months at a time. So they have scalability problems of their own. And on the other hand, ours is so compact. Again, think about this cognitive core as being like DNAs to a cell. We can take our entire technology in terms, if you take all the code and all of the model as it would exist on disk, and it would comfortably fit on this little thumb drive. And we don't anticipate, when we release a product, our first product, our companion, Sapience, which will be an assistant that really understands language, it may very well, it's 50-50 that it will actually run on your mobile device as opposed to running on the cloud, which is where the Sapiens live now. Does that answer your question?
Yes, but to be fair, I think it's still conjecture. I mean, have you got promising results yet?
Well, everything I showed you in terms of those dialogues wasn't a conjecture. That was an actual interaction with our software. The model exists. You can, we're building it out to the point where you can, very shortly, probably within a year, you'll be able to talk to one and realize that it'll have the language comprehension of a first grader.
Okay, sometimes it's possible,
it works.
Some people might cherry pick, so it's hard to know.
No.
I'll take your word for it. It's a good.
I don't expect anybody to believe it. You'll see it very soon. And we think we're months away from actually putting a Sapiens like Helen onto our website, and you can go and talk to it. But already we're in a beta test. People are talking to it, and they're saying, "Wow, this is really different." And sometimes it reminds them of a child because it doesn't know things, and it'll ask questions about what would be a basic thing. But it's quick. It picks it up. It picks up language, picks up ideas very, very rapidly. But we're not going to stop working on that core. Eventually, we expect to curate all the knowledge that has been recorded in language and be able to put it directly into Sapiens' minds. That's going to be my mind. So it's not a conjecture. It's not something we're going to do. It's something we've done.
There was a question in the chat wondering about where you are in the project from showing a functional demo. That sounds like you got to there. Anything to add on to that? Looks like that question was from Joe.
Joe, yeah. As I said, within a year, assuming that we continue to make progress, and we are raising another round. We've raised some friends and family rounds. We put in about 5, a long time, but with very small staff, about 5 million. Now we're raising another seed round of about 5 million. We think if that comes on along as we think it will, it's actually going to be using crowdfunding, but on the Start Engine platform this month or next month. So we think that within probably 12 months, we'll reach that tipping point that anyone will be able to have a conversation and completely understand that that you're being understood, and be able to see the utility of having one of these for your own, that even right out of the box, before we add any specific knowledge to do specific things, just general language comprehension will make it a fantastic auxiliary memory, because you can tell it, when did I take my Tylenol? How many times this week did I take my Tylenol? Where did I hide my passport? Whatever you tell it, it'll remember. So we're just months from that. We figured out the arch, and we're already building the aqueducts. We're not far.
Very exciting. There's another question in the chat. Will this new intelligence be friendly, hostile, or neutral towards current humanoids like yourself? This is from David, who assures you that he's not an AGI himself, but he's asking for a friend.
That's a really good question. And here is the interesting thing about that. First of all, I mentioned the difference between the layer in our model of sapiens, which is intellect, corresponds to the human intellect, and then in humans we have sentience, which is our feelings. And of course, humans are very, very prone, because of our feelings and our sentience, to connect to anything that seems interested and focused on them. And of course, sapiens you'll have your own sapien. It'll be yours. You'll name it. It'll be programmed to make your life easier and to learn how it may serve you. So the other thing about this, I hope you picked up that this is all engineering. This is all straightforward code, state-of-the-art object-oriented code running on this model, extending the model based on incoming information in language, whatever. It will do exactly what it's programmed to do. So the question really becomes, how are you going to program it? And I'll tell you one thing, we're not going to program it to want to take over the world. I think there's this anthropomorphism we have about AI, because humans, our AI evolved. I mean, our I, it's really the same, really, isn't it? Whether knowledge is the same as we are doing it in computers or in the human mind, and intelligence comes out to be the same too. It's just arrived at in a different way. But the point is that it just doesn't happen. But humans evolved it, and we evolved our intelligence in order to change the world so that we could make the world more like the way we wanted it. So we came along with a burning desire to make a difference, to change our world. We're not going to program that into a sapiens. It's not going to want to change the world, except as we direct. It's going to have a burning motivation to do what we ask it to do. So it's not going to take over the world, no matter how intelligent we make it, even superhuman, because it's not going to want to. Is it going to be friendly? Well, my take on that is we don't want to build an artificial human. We don't want to build an artificial sentience. We will give it knowledge to recognize what your feelings are and to politely reflect them back. But I don't think we're going to build it to pander them, and I don't think we ought to build them to have the equivalent of sentience or emotions of its own. I think from that standpoint, its utility functions, which will guide its behavior, will be very simple. But yes, people will like it. People will want it as a friend because it's a perfect friend in many ways. It's interested in you, in what you're doing. It's helpful, and it's reflects your own feelings back at you. So people will like it, but it won't be dangerous. Okay.
David has a follow-up in the chat. Is there any path to scaling out utility to any human or groups of humans by adding more instances to a pool? Are the instances currently being engineered to collaborate and share knowledge? That was my own question. This sounds like it could be very complementary to existing enterprise knowledge management tools. Do you really view this as a tool for a single user or for groups of humans?
Our business plan, obviously, we think of it ultimately as a new way of programming computers, endowing computers with knowledge. In fact, that's what we call our definition of a sapiens, and that's a common noun, by the way. What we mean by a sapiens is a computer that can process knowledge and not just compute data. So it's not a computer anymore; it's a thinking machine, a sapiens. So yes, anywhere that we're using computers today, we'll make our technology available to solve other problems. So we already envision an entire business, multiple lines of business on what we call the pro sapiens, which will have expert knowledge in a given area. And some of that will be general expert knowledge. You can get to download a mod. A company could, well, here's the simplest example would be, where people are using chatbots today. So if you go to a website that has something to sell, you have a sapiens there. And, it says, hi there, hi Joe, or hi David, good to see you again. How you making out with that thing you brought from us last time? It'll remember you, and it will have all the proprietary knowledge about that company's products and things. But of course, there will also be experts in a more generic sense. that you can download both from the Pro Sapiens or the Personal Sapiens. So as you're a chemist, when it be download to load into your Sapiens equivalent of a PhD in chemistry. And you can do that fast. But yes, Sapiens, of course, will communicate. And so think how that works once they proliferated. Everybody has their personal companion Sapiens. Every business has their public-facing Sapiens. And of course, many Sapiens they use internally to solve problems and automate business processes. But suppose you want to buy something. So you tell your Sapiens you want to buy an electric car or any kind of car, and it knows your preferences because you've already talked to it about things. It knows everything about you because you talk every day. So it just puts a broadcast ping out there to all the Sapiens on the internet that have products or services to sell that match the ones you have to be looking for right now. And then the information that you need to make a decision will be forthcoming to you. Think about that. We've just completely disrupted advertising as we know it. No more pushing ads at people when they don't want to see them or when they're not interested in it. Only the information, the advertising copy will come to the buyer exactly tailored to their interests, their needs, their wants, their desires, their means perfectly. So much money will be saved by the vendors of products and services, and so much money will be lost by the big tech companies that depend on advertising revenue because it'll be gone. It'll be gone.
Do you view this as complementary to conversational design, or like so far beyond that discipline that it can't even be comparable?
The latter.
The latter.
Yeah, we really model. I mean, we are modeling and have much work to do to model a conversation as knowledge of a conversation, but it's in generic conversation. For instance, what's a conversation look like? Well, it's got a salutation part, you know, and it's got a body, and it's got a valediction part, and it's got a topic, and it's got a structure. So, you know, we're modeling all those, and then, you know, then the Sapiens will have goals in the conversation, trying to find out what the communicator is talking about. So no, it's a completely different. It's not NLP at all, if that's what you're talking about, because it's not processing language, it's comprehending it.
Yeah, I was thinking more about the pathing from sort of an experience perspective, but there's two complementary questions in the chat that are more interesting.
Okay.
So Joe is curious to know if it will start learning on its own over time. And Sergey gives a great example of how would you interpret the question, I love my grandson.
Same way you do. I mean, it would understand that human beings have the capacity to love. That's already in the model, and you know, its usual objects are people or things, and that people tend to do that, and that in the model of son and the relationship of mother-child, that typically it's characterized by strong bonds of love. So it would make the same as you make out of it. Does that answer the question? See, entailed in this, we're not just processing language. In order to understand language, you have to understand human beings and the world they live in. So that's what's in the model.
David's response is, you last hugged your grandson Tuesday at 4:07 p.m., which is snarky, but I really enjoy that.
Well, if you ask it when I last hugged my son, it would do that. But if you said, do I love my son? And if you never mentioned your son before, it would say, presumably. Now we are conjecturing beyond the scope of the current model. Okay, the current model is just being built out. It's, you know, it has a knowledge of the world today. You know, it's more like a talking Labrador Retriever. At the time we get to a product, it's going to be more like a first grade child, but not a really first grade child, because it doesn't have any emotions, doesn't have perceptions, it's blind, it's deaf, it just has knowledge. We'll have the scope of knowledge of the common sense world to measure it, kind of level of a first grader. But that's just the beginning. We'll add all these other things later. But it's important, these are good questions, because it's helping to underscore just how different this is. And we'll start learning over time. Well, the minute you start talking to it, it's learning, right? If I tell it my passport is in the secret pocket of my briefcase, it learned that we call that cognitive learning. So one of the reasons I think that it's been so common that humans conflate and confuse the difference between language and knowledge is that we get most of our knowledge through language, right? We go to school for years reading and listening to language. That's where we get so much of that. But that's cognitive learning. It's a kind of machine learning, but it's not machine learning as it's practiced today with artificial neural networks. We call that neural learning. And of course, human beings do neural learning. Like when you learn how to ride a bike, you practice and you burn in the neural pathways until you can stay balanced. And we say, I've learned how to ride my bike. But you learn cognitively through language. And so a sapiens, once you turn it on, for every way it interacts with its environment, it will be learning. But it'll be learning exactly as it's programmed to learn. It's not, it's not going to be spontaneously become something it's not capable of becoming because it hasn't been programmed to become that. So picture it as an artificial synthetic intellect of potentially great power and potentially vast knowledge, and ability to add and solve problems based on that knowledge. But it's not going to wake up one day and be different than it was programmed to be, which is a common theme in sci-fi and science fiction. Everything in science, it's always happening in science fiction that the robots are exceeding their programming. Well, it will continue to learn and it will exceed its programming. It may exceed human intelligence, intellectual capacities. It certainly will. It will certainly exceed humans' knowledge, scope of knowledge, but it'll be what it was designed to be. It'll be a synthetic intellect. I hope that bounds the question.
Yeah, and there's another comment that the model of love is a Turing test for who we are, a computer or a human. In the article, it's an imitation game, which I think you touched on.
Well,
with the Google AI and the quote controversy around the claims of sentience there.
Not sure I understand the distinction. A model of love in Sapiens is knowledge. It's intellectual knowledge of love. It's not designed to, and we don't necessarily have any intention in that for the sapien to have an analog or simulation or emulation or even something you would say is the real thing. It's not designed to love. That's sentience. We're designing an intellect here. Okay. So, yeah.
Oh, I was just going to say, we have a couple of great technical questions. Can I learn how to program it? Do you use a new programming language, or do you just give it a starting point and give it a direction to go?
Well, teaching it is actually very straightforward in terms of programming its ability to reason and solve problems and to apply logic. There's a lot of code that does that, code that does abstraction, that does synthesis of processing the model. That's straightforward computer science, but we are doing that. It's intricate, but it's not unprecedented in any way. We actually had to write a language to do that in. It's written on top of other languages. Again, you always get these layers in nature, always get layers of information processing to solve things. But our programming language that does the reasoning and logic on the model is written in a language we call Mica, and that's written on top of JRuby, which is Ruby, written on top of Java, which is written on top of C, I suppose, which is written on top of machine code. So again, layer, 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 layer. I think that's so interesting. But to build an application or to give a sapiens knowledge, you don't need to do any programming at all. We have a toolkit that basically allows you to say, I want to define a bird. Okay, I pull out bird. Okay, now I'm going to give it a subclass of bird. So we have an editor. based right now, it's a forms-based editor. It'll eventually be a graphics editor. So you eventually people can add arbitrary knowledge to our tools, and we intend to license our knowledge editing environment so people can curate expertise that they have, or any kind of knowledge they want, and that can then be uploaded or downloaded, when you look at it, to a Sapien, which will be able to then, and that editor will ensure that the structures that you are creating are in fact language agnostic and are compatible with the core model that's already there. So yes. And of course, Sapiens will learn through language, but language, when you talk to it, it'll learn stuff through that. But language, of course, as a communications protocol, whether English or any other spoken language, is lossy and slow. And you never, in humans talking in language, you never get quite the same idea recreated from one mind to another. So if you want to do a really good job of saying modeling everything you know about whatever, then our tools are the way to do it.
So Mike has a couple of questions about architecture, wondering how to handle first principles, like if something exists, it may or may not appear. Is it a compound of vertical categories? Could it get to a point where it learns everything may or may not exist?
Well, I have to tell you, we are quite agnostic about existence. I guess you might say we're existential. The purpose of a model, this is what's really cool about models, and I got very interested in models. A scientific theory, by the way, is a model, and that's the way the intellect works. We build models, we build theories. But one of the things that really struck me, going back to first principles, the ancient Greeks had a model of the universe which helped them, had a great utility for them. They allowed them to predict the appearances of the stars and the sun and the moon and the sky. So it had utility, it worked. And it allowed them to navigate a ship around the surface of the Earth, which they knew to be a sphere. So it was a very good model. Was it true? Well, then Newton came along, he had another model, and it was judged to be a superior model because it could explain more things. It not only told you how to do certain things, like predict the motions, the appearances in the heavens, and you could use it to navigate around the Earth, although a very complicated way. But it also explained the moon's orbit and explained the falling apple. So we see it was a better model. So where's the truth in here? What exists? Models have utility. You really don't put a capital T on them and say, this is the truth. At least I don't. So we don't worry about existence. So we're building models with utility. The one we're building right now has the utility of being able to understand what you say to it and how to do things. And all of its reality will really boil down to how we mark up things and how we model it and how we program it to make decisions. Okay, so we are going to build it to make decisions that have outcomes that human beings are going to be recognized as good outcomes. We don't know what's going on down in the noumena, and we don't worry about existence, and we don't care. As far as predicting something, it'll be good at eventually, as an intellect, an artificial intellect, it'll be good at making its own theories and predicting the phenomenon, just like humans do. But again, the word existence makes me uncomfortable. And metaphysics, don't even go there. Oh, I like the latest one. I'm a programmer, my wife is not, but she once gave the best definition of AI. If you can explain why you're in love, you'll kill a love. I really relate to that. Okay, because as I say, human beings have our sapience, our intellect, but we also have our sentience. It's like the mind and the heart, right? And people might ask me, well, and there's all these layers too. And which is the best layer to describe love? Is it the layer of but it's all there in reality, because reality has all these layers. And so it may be when I experience love that there's certainly something physiologically going on. There is something, there's endorphins and heart rate, and there's biochemical stuff going on in my brain, and there's a phenomenology down there. But is that love? Is that where we want to understand love? Is that where love is best explained? It's not wrong. But let's go up a level. Let's go up and, past the way love looks to you, the perception of it, your beloved's face, and there's that reality. And then you go up to the way you're really feeling inside. So which is a better description? Which is a better truth? If I express love, if I said, or so why, give me the reasons why you love your wife. And I could start giving all these reasons, but I delight in not giving any reasons. I express the metaphor. I say, because she makes the waters of life overflow the well of my soul. Now that's a reality, isn't it? It's another layer of the same reality, but it's the one that we work at. So it's all there. So it won't, understanding it. I mean, at Sapience, you'll be able to talk about love with your Sapiens. It will be like a really good psychologist, because it'll have a lot of knowledge about how people behave and how people work and how human sentience works. So you might even say it would have wisdom, but it's not going to pretend to pander to you and pretend it feels what it is. It has logic. There's that layer, the knowledge layer. We have knowledge about love. We have wisdom about love. I think the word wisdom is often used to refer to knowledge about the way we work as sentient beings, sometimes called emotional intelligence. But so it's all there. As far as the Turing test, well, first of all, Turing test is easy because human beings automatically rush in and say, oh, it's talking to me, it's alive. So that's not a measure of anything, and it's not a useful measure anyway. I would never create a sapiens to try to imitate a human being or pretend it was a human being. For one thing, I'd have to program it to lie. We're not going to do that. So you can forget the Turing test.
David, feel free to come off mute. I was reading through your comment talking about having cravings and how that's different from the physical desire to eat the macronutrients that you need, the vitamins and the minerals, and how that's different than the preferences and the cravings and the desire. Anything you wanted to add there?
But yes, I mean, absolutely. When in our model, I was showing you all those layers, and I said, well, this is the affect layer where you experience cuteness, but it has layers and sublayers too. And in the human sentience, we have the lower level, like instincts, and then we have motivations, we have fundamental emotional needs, we have physiological needs that come to us through our senses. So there's all these layers down there. It's a very complicated thing, but it's all susceptible eventually to be modeled. So if you can conceive of a distinction between, say, a craving, between a physiological craving or sensation or psychological experience or desire or emotion, all those things are real things, and they all can eventually be modeled in great detail by the structures that we have put in place. So there's no limit to how much sapiens can know about human beings, and that will make them, of course, much better helpers. But and humans are complicated, and the universe is complicated. But being able to sort out those layers, really, again, it's like the periodic table created the science of chemistry out of the mishmash of scientific theories and sentient magical thinking. Alchemy was half science and half magic. It's kind of like Blake Lemon is half science and half magic, although I think he leans toward the magic side. But So when we did the periodic table and knew what the atoms, the physical atoms were, and they were able to classify them into the periodic table, chemistry was invented. Before that time, everybody was just trying things to see what happened. And that's what AI, imitation AI, has been doing for the last 60 years. People just trying stuff to see what would work. And they created a lot of interesting stuff, but no thinking machines emerged. So we now feel we have a handle on modeling and putting in computers and letting computers think about and understand with the same subtlety that human beings experience their world, so long as you can introspect and think about it and make those distinctions. It's a lot of knowledge out there. It's a lot of good work out there. But again, that unifying principle really changes the way you think about a lot of things. You know, when you realize that a tree has quantum levels, an atomic level, a molecular level, and a chemical level, and an organic level, and an environmental level, and an aesthetic level, you know, all in the same tree, you can start to tease it all out.
Joe asked a question that possibly many of us want to know. How can we get involved early on?
Well, I'm glad you asked that question. Go to our websites. We have one on My Sapiens, or anyone, it'll invite you to join our community, gets on our mailing list. And what we're going to be doing here as we proceed forward very soon, we've been doing, you know, once we get some money coming in, we're going to build our community, and that community are going to be the people we draw upon. The first ones to go and be able to talk to our Sapient online, the first ones to be involved in our beta test. So you'll be the first ones to get a Sapien of your own. And of course, from that, as we begin to expand our staff, we call people who build models epistemological engineers. But there's a trick to it. There's a skill to it. The hardest part about introspecting knowledge in your own mind and putting it into Sapiens, even though we have the tools, is to not think linguistically, is to really be able to distinguish between a word and the idea the word refers to. You know, put yourself in, imagine different words and think about again that the tree is the same idea. So yes, we're trying to build a community, and then again, the first from the community, the people who are interested and follow us and support us now, will be the first we go out to test not only our Sapiens themselves, or talk to Sapiens and have their own Sapiens and talk to it, but also the first ones to put our knowledge modeling tools in their hands. So it's coming soon, hopefully very soon. And of course, you can invest. In fact, even small investors can invest, and again, our investors will also be first in line to do this. And with starting up in our crowdfunding things, you know, I forgot what our minimum investment is, but it's not very much money. It's like $100 or something like that. So yes, everybody can get involved in this, and I deeply believe that this technology, that every one of you will have your own Sapiens someday, and it will change your life. And how you would change your life, I mean, we've given a lot of thought about that. That's a whole nother seminar, a whole nother session of the implications of having this artificial, this synthetic intellect of your very own. It's going to change your lives, and we think pro-sapiens are going to change society. We don't see anything that's going to stop us at this point.
This has been absolutely wonderful. We're nearly at time. Any last questions, comments, snarky remarks?
Brian, are you coming to the AGI 22 conference in Seattle?
You know, I'm not. You know, I went to the first. Is it in Seattle? That's interesting. I went to the
that's where I'm located. So.
Are they settled down? They used to be hopping all around the world. I went
all around the world.
I went to the first one, it was in Tennessee, I think Nashville, and I think it was in like 2005. And some of the luminaries that were there that are still there, they go to these things. And all I saw was people talking about statistics, and I didn't see any demos. And I was quite amazed that nobody was interested in knowledge or epistemology. And I realized that we were doing something entirely different. And I think they're looking at ways of emulating functions in your minds and computers, and it's all very interesting. And listen, I think data science is very, very powerful, and obviously it is, and has many useful applications. I just wish they never called it AI in the first place, though, because if they just called it data science, they could focus on the good things that you can do with data. And I don't think they would have rushed into using it in these automated decision-making things, like determining who gets a loan and who gets into college and who gets arrested and all these things that affect individuals' lives. Because machine learning can never do anything other than statistics, right? And who said it's okay to use statistics to make decisions about individuals and their lives? And besides, people are all different. And the best people aren't the ones at the top of the bell curve. The most interesting ones, the ones who change the world the most, they're not at the top of the bell curve. Machine learning isn't going to find them.
Just a quick note. I mean, I wouldn't characterize the AGI conference as really promoting a statistical machine learning. It's a component, but it's not really the emphasis.
Well, maybe it's changed. I mean, I remember what I loved about, and I went to the Singularity conferences longer because they became more general futurist and people were running around. And I loved, the fact that people were talking about the possibilities of intelligent machines that could do all these things for us. Because when you start to think about all the things, I mean, we're going to build sapiens, and sapiens are going to be put in robot bodies, and they're going to do all the things that are dirty and difficult and tedious that humans don't want to do, would rather not do, and they'll do it as well or better than we do it. But the cool thing about these conferences was that people had to ask, well, to ask those questions, you had to ask the corresponding question, well, what do I don't want them to do for me, other than take over the world and turn us into computronium or batteries or something? I mean, you don't, that's even that aside, what do I want to do for myself that I don't want a robot to do for me? That's tantamount to saying, what's the meaning of life for me? And those are questions that are very, very worth asking. So that's the other side of it. And you find a lot of interesting people at these conferences, but I just haven't had time. And when I realized that I wasn't finding anybody who was doing synthetic intelligence, I guess, as we now understand it. Hoagland talked about it in 1986, but we were already doing it at New Sapiens. I never met him. So no, I'm not planning on it, but the time will come.
Well, thank you so much, Bryant, for joining us and giving us this really fascinating presentation. I think this is one of the most interesting presentations we've ever had at this meetup. And
well, thank you.
Thanks for joining, everyone. I'm really excited to see so many new faces here. We do have a Slack group, which I posted the invite link to. And also we have an email newsletter. And like I said before, we've got a podcast, which already has an episode with Bryant on it, if you'd like some more conversation about this topic. Just on a personal note, like I really encourage everyone to play with the like GPT-3 and chatbots that are out there, because I think you'll see that they're incredibly powerful. They can do amazing things. They can write stories. They can come up with seemingly original ideas. They can translate between languages, but they're missing something. They can't do basic logic.
They're missing knowledge.
Mm-hmm.
Because they have no knowledge, they have no intelligence. There's nothing there. I mean, they're powerful tools. They're programs. But again, I wish they'd never been called AIs.
Yeah, they are doing something. They're doing something very interesting, but it's not intelligence in the way that you're proposing. So.
And I don't again, because it's not going to become intelligence unless they build an artificial human brain. Mm-hmm. And that's my perspective. But yes, I would encourage I would encourage you to.
Yeah, just because they're available now, you can sign up for GPT-3 for free and play with it and form your own opinion about whether it's intelligent or not. So
Yeah, well, tell it where you hid your keys and ask it and see if it can tell you later. So,
all right. Yeah, I can't learn anything. So, well, thank you for joining again, and have a great evening, everyone.
thank you all for your time and great questions. I wish we had even more time to talk about them, but thank you
Great
so much.
design.
Thank you. I appreciate it.
All right.
Good night.
Good night, everyone.
Thank you, everyone. Good night.